In this video, we are going to see problems in complex integration. Before that, let us learn what is simply connected region. Simply connected. First, let us see what is connected. Let us consider a curve like this. This curve is a connected curve. This is a region, so connected region or a connected curve. If we are taking any 2 points inside the region, we can draw a straight line between these 2 points. Then it is called a simply connected region. Otherwise, it is connected, or otherwise it is called a not connected. Multiply connected is nothing but two curves like this and two curves like this. This is this one curve and this is another curve. A region lies between this and this can be transformed into a connected region by drawing a strip. So we can shrink these two curves by taking this portion to this portion, and we can shrink to a point by drawing a strip. This is example for simply connected, and this is example for multiply connected without this strip, and multiply connected turned to a simply connected by drawing a strip cut. This is called a strip cut. So fine, let us see a fundamental theorem. So Cauchy's fundamental theorem. So we are going to see some problems based on Cauchy's fundamental theorem. Let us see the statement of this theorem. Statement: if a function f of z is analytic and the first derivative of the function f of z is continuous at all points inside and on the curve C, on a simply closed curve C, then the integration over the curve C f of z into dz is equal to 0. It means that the integrand part is analytic inside and on C, then the integration of the analytic function is 0. Another one, Cauchy's integral formula So if f of z is an analytic function inside and on a closed curve C of a simply connected region R, if A is any point within the curve or the contour C, then integration of f of z divided by z minus a into dz is equal to 2 pi I into f of a over the curve C. This is the Cauchy's fundamental theorem statement. I am repeating Cauchy's integral formula statement. If the given function f of z is analytic inside and on C, the function f of z is analytic inside and on C. If the point A is any point within C, then integration over f of z by z minus a into dz is equal to 2 pi I into f of a. From this statement of Cauchy's integral formula, we can derive the Cauchy's integral formula for derivative. So it is nothing but differentiate this formula. Let us call this equation number 1. Differentiate equation number 1 with respect to a. We get the first derivative of a is equal to integration over C f of z divided by z minus a raised to the power 2 into dz. If we are differentiating again this equation with respect to a again, then the second derivative of f at the point a is integration over c f of z divided by z minus a raised to the power 3 into dz. Then one more time I am differentiating the second derivative, I am getting the third derivative of f, I mean the function f at the point a is 2 into 3 integration over c f of z divided by z minus a raised to the power 4 into dz. By simplifying this, 2 3s are 6, this can be written as 3 factorial and this can be written as 2 factorial. Taking this value to left hand side, by generalizing this, the nth derivative of the given function is nothing but n factorial divided by 2 pi I into integration over c f of z divided by z minus a raised to the power n plus 1. So we can rewrite this formula for our convenient. Integration over c f of z upon z minus a raised to the power n plus 1 into dz is equal to 2 pi I divided by n factorial into the nth derivative of f at the point z equal to a. So let us solve a problem using all these formulas. So let me consider one example. My first example is using Cauchy's integral formula. Evaluate the following. Evaluate integral over the curve c z square plus 1 divided by z square minus 1 into dz, where the curve c is a circle with unit radius and center. The first option is if the center is equal to 1 and if the center is equal to I. So to solve this problem, before solving this problem, let us see how to construct a circle that you may know that z minus a, modulus of z minus a equal to r, where a is the center and r is the radius of the circle. If modulus of z equal to 1 means the center is 0 and the radius is 1, that means at origin we can get a circle like this. The coordinate axis of z plane is x and y and the center is the origin is 0 comma 0 and the radius is 1. So we get a circle like this. This is our circle. So by using that concept we can draw a circle. So the integrand is not analytic when the denominator is equal to 0. So z square plus 1 divided by z square minus 1 is not analytic, at the points z square minus 1 is equal to 0, which implies z equal to plus or minus 1. So this function is not analytic at z equal to 1. When I put z equal to 1, the denominator portion becomes 0. Anything by 0 is infinity. And z equal to minus 1 also. So minus 1 the whole square is plus 1. 1 minus 1 is 0. Anything by 0 is infinity. So the denominator portion zeros, it becomes infinity. Therefore at these 2 points this function is not analytic in general. But if our circle, let us check whether this is analytic inside and on the curve or out or not. By putting the first option is z equal to the center is equal to 1 and radius is equal to 1. That means the circle of the form z, the center is minus 1 and the radius is equal to 1. So we can easily verify whether the point z equal to 1 and minus 1 lies inside the circle or not by taking the difference between the point 1 and the center is less than the radius, means the point is lies inside the circle, or otherwise it is outside the circle. Let me do the problem. Put z equal to 1 in this circle. So 1 minus 1 is equal to 1, that means 0 less than 1. Therefore z equal to 1, the point z equal to 1 lies inside C, such that modulus of z minus 1 is equal to 1. And let us check whether the point z equal to minus 1 lies inside or not. So put z equal to minus 1, minus 1 minus 1 is equal to modulus of minus 2 is equal to 2. 2 is greater than 1, therefore my z equal to minus 1, the point lies outside C, such that modulus of z minus 1 is equal to 1. So the above function can be written as z square plus 1 divided by z plus 1 into z minus 1 equal to, the point z equal to 1, it makes the function 0 and the point z equal to 1 lies inside, but the point z equal to minus 1 lies outside. Therefore z square plus 1 divided by z plus 1 is f of z. It is analytic inside and on C, on the circle C, but z equal to 1 is lies outside C. So now taking integration on both the sides with respect to z over the curve C. So it is of the form integration over f of z divided by z, integration over C f of z upon z minus a is equal to 2 pi I into f of a. Here comparing this with this, is a equal to 1 and f of z is equal to z square plus 1 divided by z plus 1. Substitute a equal to 1 in f of z, we get f of a is equal to f of 1 equal to 1 plus 1 divided by 1 plus 1 is equal to 2 by 2, it get cancelled, equal to 1. Therefore integration over C z square plus 1 divided by z plus 1 the whole divided by z minus 1 is equal to 2 pi I into 1 equal to 2 pi I. This is the answer for the radius, the unit radius and the center z equal to 1. Similarly, we can solve for unit radius and the center z equal to I. That means our circle z minus I is equal to 1. Let us check the points z equal to 1 and z equal to minus 1 lies inside or outside. By substituting 1 here, so 1 minus I, modulus of 1 minus I is equal to square root of the absolute value of 1 minus I is real part square plus imaginary part square is equal to square root of 2, which is approximately equal to 1.414, which is greater than 1. Therefore, the point z equal to 1 lies outside C. Similarly, we can substitute z equal to minus 1 here. So minus 1 which is equal to the real part minus 1 square is also square root of 2. It is approximately equal to 1.414. This is also greater than 1. The distance between the point z equal to minus 1 and the center is greater than the radius, then the point is lies outside C. Therefore, the given function f of z equal to z square plus 1 divided by z square minus 1 completely analytic function. An analytic function inside and on C. So by using Cauchy's fundamental theorem, integration over C, f of z is analytic inside and on C, therefore the integral value is 0. So this is the answer for the second curve. Let us see another example based on this. Using Cauchy's integral formula, for a derivative, integral over evaluate, integral over C e raised to the power 2z over z plus 1 raised to the power 4 into dz, where C is the circle modulus of z equal to 2. Let us solve this problem. The function e raised to the power 2z divided by z plus 1 power 4 is not analytic at z equal to -1. Let us check whether this point lies inside or not. If the point z equal to -1 lies outside the circle, then integral value is 0. If it lies inside, being the power 4, we have to use the derivative formula, Cauchy's derivative formula. So to check whether the point z equal to -1 lies inside or not, by substituting z equal to -1 in the curve, modulus of -1 is equal to 1 is less than the radius. Therefore, z equal to -1 lies inside C. So by using Cauchy's integral formula for derivative, it is nothing but integral over C f of z divided by z minus a raised to the power n plus 1 into dz is equal to 2 pi I divided by n factorial. If it is n plus 1, it is n factorial into the nth derivative of f at the point z equal to a. So by comparing this, comparing with this, a is equal to -1, f of z is equal to e raised to the power 2z, and n is equal to 3. Now we can find the third derivative. The first derivative of f is 2 into e power 2z. The second derivative of f of z is 4 into e raised to the power 2z, and the third derivative of f is 8 into exponential of 2z, and we can find the third derivative of f at the point z equal to a is the third derivative of f at the point z equal to -1 is 8 into e power 2 into -1 equal to 8 divided by e raised to the power 2. So substituting the third derivative value here, integral over C or f of z is e power 2z divided by z plus 1 raised to the power 4 into dz is equal to 2 pi I divided by, here I said n is equal to 3, therefore 3 factorial into f nth derivative of a, that means the third derivative of f at z equal to a is 8 divided by e square. It is equal to 2 pi I divided by 2 into 3, 8 by e square, cancel the common term, so 8 pi I divided by 3 into e square. That's all the answer. And next let us solve another example similar to this. Evaluate integral over C such that modulus of z equal to 2 z square plus 1 divided by z minus 1 into z minus 2 into dz. Solution: the given function z square plus 1 divided by z minus 1 into z minus 2 is not analytic at z equal to 1 and 2. Let us check whether these 2 points lies inside or not by substituting in the given curve. The curve is modulus of z equal to 2. If I put z equal to 1, modulus of 1 is 1, 1 is less than 2, therefore z equal to 1 lies inside C. Similarly, let us put modulus of z equal to 2, put z equal to 2 here. So modulus of 2 is 2, 2 is equal to 2 lies inside and on C. There is a condition, therefore the point z equal to 2 lies on the circle C, therefore z equal to C lies on C. So far we have seen a formula that integration over C f of z divided by z minus a into dz, but we have our 2 points are here, therefore we have to separate these 2 denominator part by using partial fraction method. So we know that it is 2 pi I into f of a z square. The question is z square plus 1 divided by z minus 1 into z minus 2 equal to a divided by z minus 1 plus b divided by z minus 2. By taking LCM, b by z minus 1. The method here we are using this partial fraction is these 2 points 1 and 2 are lies inside C, but we have seen a formula only for 1 point, so we have to separate these two denominators. So the only method available is partial fraction. That is why we are using this z minus 2. Cancelling the denominators, we get z square plus 1 is equal to a into z minus 2 plus b into z minus 1. Put z equal to 1 in this equation, which implies a is equal to minus 2. When z equal to 2, a becomes 0. When we put z equal to 2, 2 minus 2 0, so this will be 5. So now substitute a equal to minus 2 and b equal to 5 in this equation. Z square plus 1 divided by z minus 1 into z minus 2 is equal to a is minus 2 divided by z minus 1 plus b, the value of b is 5 divided by z minus 2. Now taking integration on both the sides with respect to z. So equal to over the circle C such that modulus of z equal to 2. So we can separate this modulus of 2 by z minus 1 into dz plus integral 5 divided by z minus 2 into dz. Here the point z equal to 1 lies inside C. Therefore, the solution format is 2 pi I into f of a plus here also 2 pi I into f of a. And compare this, f of z equal to minus 2, a is equal to 1 here. So for a is z equal to plus 1, so we get minus 2. And for second term, f of z is 5, so 2 is also 5. Therefore 2 pi I into, for the first f of a minus 2 plus f of b is 5, so 5 into 2 pi I, subtracting this 6 pi I is the answer. That's all. Thank you.